Imagine drifting through space toward a black hole. Choosing the wrong target ensures you are shredded into subatomic particles long before you reach the darkness. A stellar mass black hole is the collapsed remains of a dead star. It contains several suns' worth of mass, yet it's been crushed into a sphere no wider than a city center. Because all that mass is concentrated into such a tiny volume, the gravitational pull changes violently over short distances, creating a steep gravitational gradient. Falling feet first, the pull on your boots becomes exponentially stronger than the pull on your helmet. Physicists call this spaghettification. You are stretched vertically like a noodle while being crushed laterally. In this scenario, tidal forces destroy you thousands of miles before you ever reach the hole's actual boundary. To survive the transit, you need a supermassive black hole. A monster like M87 star contains over 6 billion suns, spanning more than 30 billion kilometers. The tidal force at the horizon scales inversely with the mass squared. As the black hole grows, the stretching force drops. Across a human body, the gravitational gradient is practically flat. Your head and feet experience identical force, meaning you feel no stretching. Surpassing the cosmic point of no return requires seeking out the most massive object in the galaxy. While you make your descent, your friends watch from a safe distance in a nearby spaceship. Einstein's relativity shows that extreme mass warps the fabric of spacetime itself. From your friend's perspective, this warping causes your progress toward the hole to appear to slow down. As you reach the event horizon, the time dilation becomes so extreme that you appear to come to a complete, permanent stop from the outside. The light reflecting off you also struggles to escape the gravitational well. Its wavelength stretches out in a process called infinite redshift, making you appear redder and dimmer until you fade from view. To the rest of the universe, you never actually cross over. You remain a fading ghost frozen on the edge of the abyss. But your own reality is different. Your watch ticks normally, and you feel absolutely nothing as you drift across the event horizon. Looking back at the stars, you see the light of the cosmos rushing in behind you. Due to the time dilation, the history of the entire universe appears to play out in rapid fast forward. This peaceful drift eventually ends. As you plunge deeper toward the center, the tidal forces inevitably ramp up. The stretching that was absent at the horizon finally takes hold. The gravitational gradient becomes lethal, ripping your atomic structure apart as you accelerate inward. General relativity predicts this exact split. A single journey through extreme gravity creates two irreconcilable, yet equally true, physical realities. Your remains now race toward the absolute center, the singularity. Intuition suggests the singularity is a physical dot at the bottom of a dark pit, but the internal geometry of a black hole is more complex. Inside this boundary, the dimensions of space and time trade roles. Space flows toward the center, while time measures your descent. The singularity exists as a moment in time, the inescapable end for anything crossing the horizon. Attempting to steer away from the center is as physically impossible as trying to run away from tomorrow. At this point, density becomes infinite. The equations of general relativity crash, and all known laws of physics fail. This journey leads to the boundary of human knowledge, a place where time ends and the universe hides its deepest secrets.